Okay, we are going to be looking at question number 33 from section 2.3 in the calculus book. This is a problem where we need to end up graphing it, but before we graph it, we've got absolute values in the original function g of x, and we are going to make this into a piecewise linear function. By doing so, we are going to be able to graph it much easier than with dealing with the absolute value. Okay, so first thing that we need to do is find the critical value, or in this case, critical values for the function. Because we have two absolute value quantities in this original function g of x, that means that we are going to have two critical values. And in order to find the critical values, we are going to take whatever is inside the absolute value sign, set it equal to 0, and solve it. So first, I'm going to take the x minus 5, set it equal to 0, solve it to get x equals 5. Secondly, I'm going to take x minus 3, set it equal to 0, and solve it, and I get x equals 3. So I have two critical values here, 3 and 5. What that tells me is, because we have two critical values, we are going to have three different pieces to this graph for this piecewise function once we eliminate the absolute values. So we have x less than 3, we have x greater than 3 but less than 5, and we also have x greater than 5. So now we have three different pieces to worry about for our piecewise linear function. Because we have two different critical values, we are going to have three different behaviors for the function. Okay, so now we are going to have to test each one of these intervals. We've got less than 3, between 3 and 5, and greater than 5. When we test the intervals for the piecewise function, or in order to make it a piecewise function, we can plug in any value in that interval. So if I'm talking about less than 3 here, I could choose any number less than 3 and plug it in and look at the behavior of the absolute values. So a valid test point would be 0. So if I test 0, I'm going to look at the function and plug in 0. Now in this case, I have to inspect both absolute value quantities. So if I plug in 0 into the first absolute value quantity, that means that I have 0 minus 5. If I have 0 minus 5, I'm left with minus 5 inside the absolute value. Now the absolute value then takes the opposite of it. And again, the reason I say opposite is because we need that language, because we can mimic taking the opposite with the subtraction sign, the opposite sign. Okay, so what's that telling me is, for the first quantity, absolute value of x minus 5, I can drop the absolute value sign and replace it with the negative sign. So now I have g of x equals the opposite of x minus 5. Okay, I'm always going to have the subtraction sign because that's what the original function had in it. Okay, but now I want to test the second absolute value quantity with that same test point of 0. Okay, so 0 minus 3, that means I have a negative 3 inside the absolute value, which tells me that the absolute value is going to take the opposite of it. We are going to mimic that behavior with the opposite sign. So now I have g of x equals opposite of x minus 5 minus the opposite of x minus 3. Okay, so what that means is we have g of x equals opposite x plus 5. The negative negative is going to make a positive, so I'm going to say plus x minus 3. Take it one more step. I have g of x equals 2. Once we've done that reduction for g of x, for that first piece, we end up with 2 as a result. Making some more room here so it's a little clearer. Okay, so g of x equals 2. So that's the first piece. G of x equals 2, and that's when x is less than 3. Okay, so as we said before, we have an interval of greater than 3 but less than 5. Now chances are what this is going to do is make one of the absolute values the opposite, or we're going to need the negative sign for one of them, okay, as opposed to both of them. We have both of them over here needed opposite signs. In the middle interval, we're going to need one of them with the opposite sign. Okay, so we're testing now between 3 and 4. With integers, there's only one integer in between, so the easiest test point or the simplest test point is going to be 4. But again, you could choose any value that is between 3 and 5. Okay, and why we're doing this is we're going to then inspect the equation and see where I need to place a negative sign, if at all, in place of the absolute value. So, first quantity, absolute value of x minus 5. If we plug 4 into that, I've got 4 minus 5, or a negative 1, inside that absolute value. The absolute value will take the opposite of that and make it a positive 1 in this instance. So we are going to need the negative for the first part. For the second one, if we plug in a 4, I've got 4 minus 3. That's a positive 1. The absolute value is not going to do anything to that. So we're just going to drop it in this middle piece. So that means then that our middle piece is going to be g of x equals the opposite of x minus 5 minus, that was again part of the original problem, x minus 3. So for the second part, in this interval, nothing happens with the absolute value. The absolute value does not do anything to the values. So I just dropped it. But again, I have to make sure that I distribute my negatives appropriately. So in the middle here, we've got negative 2x plus 8. Negative 2x plus 8. Okay, one more piece to go. And again, this piece is when we are greater than 5. So just to kind of foreshadow for a bit, we've taken the opposite of both of the absolute values here. We took the opposite of one of the absolute values in the middle. So my guess is we're going to not need an opposite sign at all, and we're just going to drop both of the absolute value signs for the third piece here when x is greater than 5. Okay, so again, a test point. Any value greater than 5. Simplest one would be 6. 6 minus 5 into the first absolute value, we get a 1. Absolute value doesn't change that. 6 minus 3, we get a 3. The absolute value doesn't change that. So again, for the piece bigger than 5, the absolute value might as well not be in the problem. So we are just going to drop it. But again, make sure you distribute that negative sign over that x minus 3 quantity. Okay, so in this one, we end up with g of x equaling negative 2. Negative 2. Okay, so we've got enough now to draw or write this up as a piecewise function. And again, this one is piecewise linear as well. We have a horizontal line at 2. We've got an oblique line with a slope of negative 2 between them. And then we're at another horizontal line of negative 2. So I'm going to redefine g of x as a piecewise function. In this case, we have three pieces. We have less than 3. We have between 3 and 5. We have greater than 5. Okay, so we need to put some equal signs with these numbers, so to speak, our critical values. I want to include it somewhere, the 5 and the 3 here. Now, in this case, it does not matter where we put the equal sign, so to speak, or which piece we put the equal sign at, just as long as you choose one. And again, the reason for that is that this function is piecewise, and it was derived from this original function with absolute values in it. This original function with absolute values is continuous. The absolute value function is continuous in itself, and linear functions are under the branch of polynomials, and they are continuous over the entire real number set as well as the absolute value. In this case, we have the composition of continuous functions is continuous. So once we realize that for the original function g, we can then make sure that we include an equal sign for those critical values on one piece. I wouldn't want to overdo it and include them on both pieces because, again, we want to be under the rules of function language here. Okay, so now we need to graph this. And we've got 3 different pieces now to graph. We've got 2, the negative 2x plus 8, and the negative 2. And we've got some different values, so to speak. But because we have these 2 horizontals here at 2 and negative 2, this graph is probably going to be pretty straightforward once we kind of get to our values. So I've got my axes set here. Okay, and again, 3 and 5 are really what I want to talk about. So I've kind of made my positive x a little longer than the other pieces just to kind of make sure that we can see enough of the graph to get what this is looking for. Okay, so again, from when we're less than 3, we're at 2. So that means I have a horizontal line that's going to, in a sense, stop at 3, 2. So I've got this horizontal piece when I am less than 3. Okay, I'm going to jump to the third piece, the negative 2. Okay, because again, that negative 2 is when we're greater than 5. Okay, so I need a couple of markers on my negative area as far as the negative 2 is concerned. Okay, and that happens to the right of 5. So 3, 4, 5, I'm at negative 2 now. So I had this point 3, 2, and then I have this other point 5, negative 2. And from there, I know that I have a horizontal line. Okay, so in between those, we have this negative 2x plus 8 function. I'm basically going to be connecting the dots. Now, if I've drawn this accurately, we're again graphing y equals negative 2x plus 8 here. If I did have an x-intercept, it would be at 4. So hopefully my graph does a decent job of that. And it looks like it does. Goes right through at that mark 4, 0. So the piece that's in here, this is y equals negative 2x plus 8. Y equals negative 2x plus 8. I think that got cut off the screen. So y equals negative 2x plus 8 is right there. Okay, and again, that is that middle piece connecting those 2 horizontal or constant lines. Y equals negative 2, 2x plus 8 is in the middle. I've got y equals 2 here, goes down to y equals negative 2. And again, this one is piecewise linear because the pieces are lines. Okay, so we have a piecewise linear function. We made the pieces from pulling it apart from the absolute value. Okay, and again, this is a good skill to have for calculus, for pre-algebra. Okay, and again, we have a piecewise linear function, 3 different lines. We had two critical values, which gave us 1, 2, 3 different pieces for that function. From there, we've got some algebra. We didn't have to worry about continuity, where to put those equal sign on those critical values because it was pulled from a continuous function. So that was question number 33 from section 2.3.